At the heart of every galaxy lies a brilliant, terrifying secret. We call them supermassive black holes, but that name barely scratches the surface of what they truly are. By the end of this journey, you will know 25 astonishing secrets that rewrite the rules of our universe. We will uncover how these monsters can be brighter than 1,000,000,000,000 suns, how they might have existed before galaxies themselves, and how they could be hiding the key to a theory of everything. What is the most shocking truth waiting in that cosmic darkness? Our very first secret shatters the most basic assumption we have about these objects. A supermassive black hole is not actually black. The name itself is a cosmic misdirection, a trick of scale and perspective. True, the black hole's point of no return, its event horizon, is the darkest place imaginable, a one-way door from which not even light can escape. But step back and you witness the single most brilliant spectacle in the known universe. The secret lies in what is happening just outside that ultimate boundary. Imagine a cosmic whirlpool of unimaginable fury, a disk of gas, dust, and stellar debris spiraling inward at nearly the speed of light. This is the accretion disk. As this material is pulled by the black hole's immense gravity, it does not fall in quietly. Particles collide, creating immense friction. Magnetic fields, twisted into knots of unbelievable power, channel jets of energy and act like cosmic brakes. This violent chaos heats the material to temperatures of millions, even billions of degrees. It glows not with visible light, but with the fierce, penetrating radiation of X-rays and gamma rays. When a black hole is actively feeding, this process transforms it from a dark pit into a beacon of staggering power. We call these active, feeding black holes quasars. A single quasar, powered by a supermassive black hole no wider across than our solar system, can outshine the combined light of every single star in its host galaxy. It is a lighthouse whose beam cuts across billions of light years. So the next time you picture a black hole, do not picture a silent, dark void. Picture instead the blinding, furious heart of a cosmic forge, a paradox where the greatest darkness gives birth to the most brilliant light. This brilliance leads us directly to our second, and perhaps more profound, secret. The origins of these cosmic giants are a complete mystery. We know they exist at the hearts of nearly all large galaxies. We can see them shining from the farthest reaches of the cosmos, from a time when the universe was just a baby, only a few 100 million years old. And that is the problem. How did something so massive, requiring millions or even billions of suns worth of material, gather itself together so astonishingly fast? This is the great seed problem in cosmology. If a supermassive black hole grows by steadily feeding, like a snowball rolling downhill, it needs an enormous head start. It needs a seed, but what kind of seed could possibly explain what we see? The first theory suggests a dramatic beginning. Imagine, in the early universe, a vast, pristine cloud of hydrogen and helium gas. But this is no ordinary cloud. It is so massive and dense that it skips the step of forming stars entirely. Instead, under its own immense weight, it collapses directly, catastrophically, into a black hole. This direct collapse would create a heavyweight seed from day one, a monster already thousands of times the mass of our Sun, giving it a huge advantage in the growth race. The second theory takes a more traditional path. Perhaps the first generation of stars were true behemoths, hundreds of times more massive than our Sun. These stars would have lived fast, furious, and short lives, exploding as supernova and leaving behind stellar black holes as seeds. But then, something extraordinary must have happened. These smaller seeds would have needed to merge and feed at a rate that defies our current understanding. A runaway feast in the dense, young universe to reach supermassive sizes so quickly. Then there are the exotic possibilities. Could the seeds have been planted even earlier, in the first chaotic moments after the Big Bang itself? tiny fluctuations in the density of the newborn cosmos might have crumpled regions of space directly into black holes. These primordial black holes could have been wandering the universe since nearly the beginning, acting as ready-made seeds for the giants we see today. This is not just an academic puzzle. The nature of these first seeds dictates how galaxies themselves were built. It challenges our models of cosmic evolution and forces us to question what was possible in that ancient, violent dawn. The hunt is now on, with eyes like the James Webb Space Telescope peering back to the universe's first light. Astronomers are searching for the faint, red glow of those very first supermassive black holes and their host galaxies. They are looking for the birth certificates of the cosmos's most powerful engines. What they find will rewrite the first chapter of our universal story. But this incredible power comes with a catch. Our third secret reveals a startling truth about these cosmic engines. They can starve. A supermassive black hole is not always a brilliant quasar. In fact, for most of its existence, it might be quiet, dark, and almost dormant. This difference comes down to one simple thing: food. Picture a sleeping dragon in its cave, surrounded by treasure but with nothing left to burn. That is the state of a quiescent or quiet supermassive black hole. The most famous example sits right in our own galactic backyard. Sagittarius, a star, the supermassive black hole at the heart of the Milky Way. It is a behemoth with over 4 million times the mass of our Sun, yet it emits only a faint whisper of energy. Why? Because there is simply not enough gas and dust falling into it. The space around it is relatively clean, swept clear by ancient stellar winds and past feeding frenzies, without a steady stream of material to form that furious, glowing accretion disk. The black hole has nothing to power its cosmic fireworks. The jets shut down, the blinding light fades. All that remains is the silent, gravitational grip of the monster itself, detectable only by the frantic orbits of stars whipping around its invisible point. Astronomers call an active, feeding black hole an active galactic nucleus, or a GN. This is the umbrella term for all the brilliant phenomena, including quasars. But when the fuel supply is cut off, the GN switches off. The beast slumbers. This cycle of feast and famine is fundamental to a galaxy's life. A major merger with another galaxy can send vast rivers of gas streaming toward the center, waking the black hole in a spectacular outburst. That outburst, in turn, can blow away the remaining gas, shutting off star formation across the galaxy and putting the black hole back to sleep. It is a self-regulating cosmic thermostat. So the next time you look at the peaceful center of our Milky Way, remember the potential sleeping there. Sagittarius, a star, is not dead. It is merely waiting, a gravitational trapdoor, for its next cosmic meal to wander too close. That quiet slumber is a deceptive calm. Our fourth secret reveals these monsters are not passive residents, but active architects, wielding ultimate control over the fate of their entire galactic home. This power comes from a process astronomers call feedback, and it is the most important relationship in galaxy evolution. When a black hole feeds, it does not just consume. It gives back with terrifying force. The energy erupting from its poles in those relativistic jets and the intense radiation from its accretion disk blast out into the surrounding galaxy. This energy acts like a cosmic blowtorch, heating the vast reservoirs of cold gas that would otherwise collapse under gravity to form new stars. This is negative feedback. The black hole, in its fury, shuts down the very nursery that could feed it in the future. It is a self-imposed diet, a way of preventing itself from growing too large too fast. Without this regulation, galaxies would burn through their fuel in a frenzy of star birth, leaving behind dead red husks. Our own Milky Way may owe its relatively peaceful, steady pace of star formation to past outbursts from Sagittarius, a star. But the story has another side, a strange and beautiful contradiction. Those same violent outflows can also be creative. As a supersonic jet plows through interstellar space, it does not just heat gas. It can also sculpt it. The leading edge of the jet creates immense shock waves, walls of pressure that slam into galactic gas clouds. Sometimes this shock is so powerful it crushes the cloud, compressing it past the point of no return and triggering a burst of new star formation. This is positive feedback. In these rare and spectacular cases, the black hole becomes a cosmic gardener, planting seeds for new stellar generations even as it destroys the conditions for more. We see this in stunning detail in galaxies like Messier 51, the Whirlpool galaxy, where jets from its central black hole appear to be directly triggering the birth of bright, young star clusters along their path. So the supermassive black hole is not a king on a throne. It is the master regulator, the beating heart that sets the rhythm for its entire galaxy. Its outbursts are the thermostat, the on-off switch for cosmic creation. One moment it is a destroyer of potential, the next an unlikely creator. This delicate, violent balance between heating and compression, between destruction and birth, is what shapes the beautiful diversity of galaxies we see in the night sky. That delicate balance between creation and destruction can tip into pure, unadulterated violence. Our fifth secret exposes the ultimate fate for any star that dares to wander too close. A supermassive black hole can and does eat stars. Astronomers call these catastrophic encounters tidal disruption events, and they are among the most violent spectacles in the modern universe. The drama begins with a star, perhaps one from a dense cluster near the galactic center, whose orbit takes it on a fatal trajectory. As it approaches, the difference in gravitational pull between the side of the star facing the black hole and the side facing away becomes overwhelming. This tidal force, the same force our moon uses to gently tug on Earth's oceans, is amplified to a cosmic extreme. The star is not simply pulled apart. It is stretched. In a process vividly known as spaghettification, the star is drawn out into a long, thin stream of glowing gas, a stellar noodle wrapping around the black hole's point of no return. But not all of this material is doomed. The physics of this chaotic disruption is messy. While much of the stellar debris falls past the event horizon, vanishing forever, a significant portion is flung outward at incredible speeds or settles into a temporary, searingly hot accretion disk around the black hole. This sudden infusion of fresh fuel triggers a brilliant flare of light, a final scream from the consumed star that can outshine its entire host galaxy for months. This flare is not just visible light. It erupts across the entire electromagnetic spectrum, from radio waves to energetic X-rays, a beacon of stellar annihilation. For astronomers, these events are a precious gift. A dormant, invisible black hole, quietly lurking in a distant galaxy, suddenly announces its presence and its properties with this single, terrible act. By watching how quickly the flare brightens and fades, scientists can estimate the black hole's mass. By analyzing the light signature, they can learn about the composition of the devoured star. Each tidal disruption event is a fleeting, natural laboratory, offering a direct measurement of a monster we could never see otherwise. It is a stark reminder of the raw power residing in galactic centers, where the serene dance of stars can, in an instant, become a single, brilliant course in a cosmic feast. The star's final scream is just one way a black hole broadcasts its power. An even more spectacular display erupts from its poles, where physics is pushed to its absolute limit. Secret number 6. These monsters launch jets of plasma that can span entire galaxies. When a supermassive black hole is actively feeding, its furious accretion disk acts like a cosmic dynamo. The gas is not just hot, it is magnetized, and as it swirls at relativistic speeds, it twists those magnetic field lines into knots of unimaginable tension. Think of winding a rubber band tighter and tighter, storing vast amounts of energy. Now channel all that pent-up force along the axis of the black hole's rotation, its poles. Here, the magnetic fields act as the universe's most powerful particle accelerator. They grab charged particles from the seething disk and sling them outward in two narrow, opposing beams, like the beams of a lighthouse turned up to a catastrophic scale. These are relativistic jets. The particles in these jets are accelerated to over 99% the speed of light. They are not fire, but a superheated soup of electrons and protons, a plasma so energetic it glows with a brilliant synchrotron radiation across millions of light years. And their scale is utterly incomprehensible. These jets do not merely flicker, they blast outwards in a continuous torrent, punching through the heart of their own galaxy and roaring far out into the emptiness of intergalactic space. They can stretch for hundreds of thousands, even millions of light years. That means a jet launched from a black hole could be 10 times longer than the entire Milky Way is wide. As these titanic beams plow through the thin gas that floats between galaxies, they do not slip through quietly. They carve. The leading edge of the jet slams into the intergalactic medium like a cosmic plow, pushing the material aside and inflating gigantic, radio-emitting bubbles on either side of the galaxy. We see these colossal structures as giant lobes, often dwarfing the galaxy that created them, silent testimony to an outburst that may have lasted for millions of years. This is where a single black hole's influence transcends its home. In the dense neighborhoods of galaxy clusters where thousands of galaxies swarm together, these jets become the ultimate climate control. The superheated gas inside the bubbles they create rises, preventing the cooler gas at the cluster's core from collapsing to form new stars. It is feedback on the grandest possible scale, where a single engine at the heart of one galaxy can regulate star formation for an entire galactic metropolis, keeping it from burning out too quickly. These jets are the black hole's most far-reaching voice, a scream of raw physics written across the cosmos in letters of energy 100,000 light-years long. The sheer power of those jets is born from the physics of the singularity, a point of infinite density where our understanding of the universe breaks down completely. And it is here, at this ultimate boundary of knowledge, that we find our seventh secret, the most speculative of all. The mathematics suggests these monsters might be portals. When Albert Einstein published his theory of general relativity, his equations did more than just describe gravity as the curvature of spacetime. They opened a door to possibilities that seem ripped from science fiction. Other physicists like Nathan Rosen explored these equations and found a tantalizing solution. A black hole's intense gravity, they realized, could in theory warp spacetime so severely that it might not simply create a bottomless pit but a bridge. This hypothetical structure is known as an Einstein-Rosen bridge, though you likely know it by its more popular name, a wormhole. The idea is breathtaking. The singularity at the heart of a black hole might not be an end. Instead, it could be a tunnel, a shortcut connecting two distant points in our universe, or something even more radical, a connection to an entirely different universe altogether. On the other end of this cosmic subway, the equations suggest might be the opposite of a black hole, a theoretical object called a white hole. Where a black hole is a point of no return, a white hole would be a point of no entrance, a place where matter and energy can only erupt outward, perhaps from another reality into ours. It is a perfectly symmetrical, beautifully elegant idea hidden within the math, but before you plan a journey, you must understand the crushing caveats. The wormholes described by these classical equations are almost certainly not traversable. They are predicted to be incredibly unstable, snapping shut in an instant unless held open by a form of exotic matter with negative energy density, something we have never observed. And then there is the singularity itself. Even if the tunnel existed, anything passing through would be stretched and shredded by those same tidal forces that spaghettify a star long before it could reach any hypothetical exit. So is a supermassive black hole a gateway? Practically, almost certainly not. The universe seems to abhor such shortcuts, but the profound secret is that the mathematics, our best description of reality, does not forbid it. It whispers that the darkest pit might be a locked door, and the key awaits in a theory that unites gravity with the quantum world. The singularity is not just a place where physics ends, but where imagination, guided by the cold logic of equations, truly begins. That mathematics of a singularity is a realm of pure theory, but the feeding habits of these giants are governed by a very real physical law. Even a supermassive black hole has a maximum appetite. This is the Eddington limit, a cosmic speed bump written in the fundamental balance of light and gravity. Picture a star or a vast cloud of gas falling toward the black hole's event horizon. As it spirals in and heats up, it doesn't just glow, it erupts with radiation. This radiation exerts a tangible outward pressure, a force of light pushing back against the infalling material. The Eddington limit is the precise point of equilibrium, where the outward push of this radiation perfectly balances the inward, crushing pull of the black hole's gravity. It is the ultimate cosmic diet plan. If the black hole tries to feed faster, gulping down more material than this limit allows, the resulting radiation becomes so intense it acts like a stellar wind on a catastrophic scale. It literally blows the surrounding gas and dust away, cutting off the black hole's own food supply. The feast is over before it can truly begin. This fundamental limit explains why we don't see quasars that are infinitely bright. It puts a ceiling on their luminosity and, by extension, on how quickly a black hole can grow. A monster can't simply gorge itself to infinite size in a short cosmic time. It must feed at a measured, regulated pace, often interrupted by these self-induced famines. Think of it as a safety valve for the universe. Without the Eddington limit, a supermassive black hole in a gas-rich environment could consume without restraint, potentially growing to such an absurd size it would destabilize its entire galaxy far too quickly. This limit forces a rhythm of feeding and feedback, a cycle of outburst and quiescence that allows galaxies to evolve over billions of years. It is a quiet rule written in physics that ensures even the most voracious cosmic predators cannot completely devour their home. The ultimate limit on their growth is a rule written in light, but their most profound conversations are written in the fabric of space itself. Secret 9 reveals these monsters can sing. When we think of observing the universe, we think of light, from the gentle glow of stars to the fierce blast of X-rays. But supermassive black holes have a deeper, more fundamental voice, one that travels not as photons, but as ripples in the very geometry of reality. These are gravitational waves, first predicted by Einstein and finally detected a century later from collisions of stellar mass black holes. Yet the song of the supermassive giants is different. It is not a brief chirp, but a deep, persistent hum that fills the cosmos. This hum arises from the most epic dance imaginable. When two galaxies merge, their central supermassive black holes are drawn together by gravity, eventually forming a binary pair. These two incomprehensibly heavy objects, each billions of times the mass of our Sun, begin to orbit one another. As they circle, they churn the space-time around them like the paddles of a cosmic mixer, sending out relentless waves that propagate across the universe at the speed of light. These waves have an incredibly low frequency, with wavelengths so long it can take years, even decades, for a single ripple to pass by. You could not build an instrument on Earth large enough to detect them. So astronomers built one out of stars. The effort is called a pulsar timing array. It relies on nature's most perfect clocks, millisecond pulsars. These are the rapidly spinning, ultra-dense cores of dead stars, beaming out flashes of radio waves with a stability that rivals our best atomic clocks. Scientists meticulously monitor the precise arrival times of these flashes from an array of pulsars scattered across our galaxy. The concept is breathtakingly simple in its ambition. A passing gravitational wave, a ripple in space-time, will very slightly stretch and then compress the distance between Earth and a given pulsar. This minuscule change, smaller than the width of an atom over thousands of light years, will cause the pulsar's clock-like flashes to arrive a tiny bit early, then a tiny bit late. By tracking the correlated pattern of these timing deviations across dozens of pulsars, astronomers can tease out the faint signature of the gravitational wave background, the combined hum of every supermassive black hole binary in the universe. It is like listening to a stadium full of people humming different notes, and from that cacophony, discerning the dominant chord of the cosmos. Recent data hints that we are on the verge of hearing this chorus for the first time. This is not just a new way to see the universe, it is a new way to listen. We are tuning our ears to the low-frequency vibration of space-time itself, hoping to hear the endless, slow-motion waltz of invisible giants, a testament to the epic mergers that have shaped the galactic landscape since the dawn of time. That low-frequency hum is a whisper compared to the violent distortions happening right at the source. Secret 10 reveals the ultimate power of a spinning monster. It does not merely sit in space, it actively twists the universe around it. This phenomenon is called frame dragging, and it is one of the most direct, extreme validations of Einstein's vision. A non-spinning black hole warps space like a heavy ball placed on a stretched rubber sheet, but a rotating black hole, described by the mathematics of Roy Kerr, is like that same ball set into a furious spin. It doesn't just create a dip, it drags the very fabric of the sheet around with it. Space-time itself becomes a cosmic whirlpool, forced to rotate with the black hole. This creates a bizarre region just outside the event horizon called the ergosphere, a place where the rules of reality as we know them break down. Within the ergosphere, the dragging of space-time is so powerful that nothing, absolutely nothing, can remain stationary. Not a spaceship, not a particle of light, not even a hypothetical astronaut anchored with impossibly strong rockets. Everything is caught in the current, compelled to move in the direction of the black hole's spin. It is a cosmic mandate: you must orbit. This is not a matter of gravity being stronger, it is the geometry of the universe being set into motion. To stand still here would require moving faster than light backwards, which is impossible. The very concept of standing still loses all meaning because space-time itself is flowing like a river around the central cataract. The ergosphere is not a place of destruction, but of immense harnessable energy. Theoretical work by Roger Penrose showed that a particle entering the ergosphere could, under the right conditions, split in two. One fragment could fall into the black hole, while the other escapes with more energy than the original particle had. This Penrose process effectively steals rotational energy from the black hole itself, slowing its spin. It is a theoretical blueprint for a galactic-scale power plant, drawing energy directly from the twisted spacetime of a spinning singularity. While we cannot build such an engine, nature might. The intense magnetic fields and particle collisions within the ergosphere are likely responsible for launching and collimating those incredible relativistic jets, channeling the black hole's stolen rotational energy into beams that cross intergalactic space. So a supermassive black hole is not a static hole. It is a dynamic, spinning top that ensnares the fundamental stage of the universe, forcing it to dance to a single, relentless rhythm. The very heart of a galaxy might not be where you expect. Our 11th secret confronts a fundamental assumption we often make about these cosmic giants. A supermassive black hole is not always perfectly centered. It can wander. The image of a serene, stationary monster sitting at the exact geometric middle of its galaxy is often wrong. These black holes can be kicked, nudged, or slung from their central thrones, becoming cosmic drifters within their own stellar metropolises. The primary culprit for such a dramatic displacement is the most violent event a galaxy can experience, a merger. When two galaxies, each with its own central black hole, collide and finally unite, their black holes will eventually form a binary and spiral together. As they merge, the emission of gravitational waves is not always perfectly symmetrical. If the merger is lopsided with black holes of unequal mass or spin, the final single black hole can receive a powerful kick from the gravitational waves themselves. It is a cosmic recoil like the kick from a rifle, but on a scale that defies belief. This recoil can launch the newborn supermassive black hole out of the galactic center at speeds of thousands of kilometers per second, fast enough to escape the galaxy's core entirely, though not usually fast enough to escape the galaxy's overall gravitational pull. The result is a recoiling or wandering black hole, a displaced monster orbiting within the galactic halo, far from the dense star clusters it once ruled. We have evidence of these exiles. Astronomers have spotted brilliant quasars, the signatures of actively feeding black holes, shining from locations far offset from the visible center of their host galaxies. In some cases, the black hole might be on a long, elliptical orbit, destined to eventually sink back to the center over hundreds of millions of years through a process called dynamical friction, where its gravity drags on surrounding stars, slowing it down. In other, rarer cases, the kick might be so strong the black hole is ejected into intergalactic space, becoming a rogue, homeless giant drifting through the cosmic void. This wandering has profound implications. A displaced black hole cannot effectively regulate its galaxy through the normal feedback processes. Its jets and radiation would blast out into empty intergalactic space, not into the star-forming gas clouds of its host. Its growth might be stunted, cut off from the rich fuel reserves of the central reservoir. Furthermore, its gravitational tug would distort the orbits of stars in its new neighborhood, leaving a subtle, chaotic fingerprint in the galaxy's structure. Finding these wanderers helps astronomers reconstruct a galaxy's violent history, like finding a bullet embedded in a wall, telling the story of a long-past collision. The center of a galaxy, then, is not always a fixed address. It can be a destination, a temporary perch, or a place a black hole is still falling toward. A reminder that even the most massive objects are subject to the unpredictable violence of a dynamic and evolving universe. These wanderers hint at a deeper, more fundamental disruption to our cosmic story. Our 12th secret confronts the very timeline of creation. Supermassive black holes might have existed before the galaxies that now host them. This idea turns the traditional narrative of galaxy formation completely on its head. For decades, the prevailing model was beautifully simple. First, vast clouds of dark matter and gas would coalesce under gravity, slowly spinning and flattening into a protogalaxy. Stars would ignite within it. Only then, over much longer timescales, would gas funnel to the center, pooling and collapsing to form the central black hole. The galaxy came first, and the black hole grew within it, a later addition to the cosmic city. But the universe, as seen through our most powerful telescopes, tells a different story. We have now observed quasars, the brilliant beacons of actively feeding supermassive black holes, shining from the very edge of observable time. They exist in an era when the universe was less than 1 billion years old, a mere infant. The most distant quasar we have found, with a black hole over 1 billion times the mass of our Sun, existed when the cosmos was only about 670 million years old. That is the real puzzle. How could a black hole grow to such an immense size so quickly if it had to wait for a mature galaxy to form around it first? The timescale seems impossibly short. This discovery has ignited a fierce chicken or egg debate in cosmology. Which came first, the galaxy or the black hole? One radical school of thought suggests the black hole was the seed. In this scenario, a direct collapse black hole, a primordial heavyweight, forms incredibly early in a dense knot of the universe. Its immense gravity then acts as a gravitational anchor, pulling in vast amounts of dark matter and gas far more efficiently than the surrounding space. The black hole becomes the nucleus, the heart around which the first stars and the galactic structure itself assemble. It is not a resident of the city, it is the foundation stone upon which the city is built. The opposing view holds that some ultra-dense, fast-collapsing regions in the infant universe could form both a stellar nursery and a black hole seed in a frantic, simultaneous rush. In this chaotic birth, material streams to the center at a phenomenal rate, feeding the newborn monster so rapidly it defies the Eddington limit, allowing for a brief period of supercharged growth. The galaxy and its black hole would be twins born in the same violent event, one immediately beginning to regulate the other. This is not just academic curiosity. The answer reshapes our understanding of cosmic evolution. If black holes came first, they were not just inhabitants of the early universe, they were its architects, their growth and feedback dictating the very first stages of galaxy formation. Their fierce light might have been the first major source of radiation to reionize the cosmos, tearing apart the primordial hydrogen fog and making the universe transparent to light. We are peering back to the first pages of the cosmic storybook, and the opening lines are not about gentle clouds of gas. They are about the sudden, brilliant ignition of monsters whose shadows may have shaped everything that came after. This hidden reservoir of rotational power is one of their most astonishing secrets. A black hole's mass commands attention, but its spin is a colossal hidden battery. The energy locked within a rapidly rotating supermassive black hole is almost beyond calculation, dwarfing the raw power of its mass alone. This energy is not stored in the singularity, but in the very motion of space-time around it, within that whirling region of no escape, the ergosphere. Here, space itself is dragged around at nearly the speed of light, and this churning vortex holds the key to the universe's most powerful natural engines. The theoretical mechanism to tap this cosmic battery is known as the Penrose process. Imagine a particle, perhaps from the surrounding accretion disk, that ventures into the ergosphere. The laws of physics in this twisted zone allow for a remarkable theft. The particle can split in two. One fragment carrying negative energy is doomed to fall across the event horizon. The other fragment, now imbued with more total energy than the original particle had, is flung back out into the universe. Where did that extra energy come from? It was stolen directly from the black hole's rotation. The infalling fragment with negative energy effectively acts as a brake, slowing the black hole's spin by a minuscule amount. The rotational energy lost is precisely the energy carried away by the escaping fragment. It is a perfect, if theoretical, cosmic transaction. While we cannot build a Penrose engine, nature absolutely does. This process, or something very much like it involving magnetic fields and plasma, is believed to be the fundamental power plant for those spectacular relativistic jets. The furious spin of the black hole twists the magnetic fields anchored in its accretion disk, channeling this extracted rotational energy into two narrow, focused beams that scream across the cosmos. A rapidly spinning black hole is therefore a far more efficient and powerful cosmic engine than a stationary one. It can convert a much larger fraction of the infalling mass into pure energy, approaching an efficiency of up to 40%, compared to the meager 1% efficiency of nuclear fusion that powers stars. This is why the fastest spinning monsters, often found in the most brilliant quasars, can launch jets that punch through entire galaxy clusters. Their spin is the winding key, and the universe bears the scars of their unleashed power. But the spin that powers such incredible engines could, in theory, lead to a reality so bizarre it might shatter physics itself. Our 14th secret ventures into the most radical mathematical possibility of all. A supermassive black hole could theoretically be naked. This idea stems from pure mathematics, from exploring the extreme solutions to Einstein's own equations of general relativity. We have always described a black hole as having two key parts: the central singularity of infinite density and the event horizon that shrouds it, a one-way membrane hiding the singularity's impossible physics from our universe. But the equations suggest a third, almost heretical configuration. If a black hole possesses an extremely high electric charge, or more likely, rotates at the absolute maximum possible speed, the mathematics can change. The event horizon, that crucial veil, might simply vanish. The result would be a naked singularity, a point of infinite density and zero volume, exposed for the entire universe to see. There would be no point of no return, no protective horizon. The laws of physics as we understand them, which break down completely at a singularity, would be on full catastrophic display. You could, in principle, fly a spaceship right up to it, observe it, and then fly away. The implications are terrifying to a physicist. A naked singularity would be a place where predictability, the very foundation of science, ceases to exist. Our equations for gravity become meaningless. Cause and effect could unravel. Information could be created or destroyed at random. It would be a cosmic loose cannon, a glitch in the simulation of reality with consequences we cannot possibly foresee. This prospect is so unsettling that the renowned physicist Roger Penrose proposed the cosmic censorship conjecture. This is not a law, but a deeply held belief that nature abhors such exposure. The conjecture states that the laws of physics always conspire to cloak any singularity behind an event horizon, protecting the sanctity of causality in the rest of the universe. It is nature's firewall, ensuring that the breakdown of physics remains locked away, unable to infect the predictable cosmos we inhabit. So far, every observation supports cosmic censorship. We have never seen a candidate for a naked singularity. The universe seems to prefer its monsters clothed in darkness, yet the secret persists in the cold, elegant mathematics. The possibility, however remote, remains a tantalizing whisper from Einstein's equations, a reminder that our understanding of these cosmic giants is built on a foundation that might, under the most extreme conditions we can imagine, allow for a reality far stranger than any event horizon can contain. The mathematics of a naked singularity hints at creation from chaos, but the true creative power of these giants is far more tangible. Secret 15 reveals they might be cosmic forges, responsible for creating the heaviest elements in the universe. Think of the gold in a wedding ring or the platinum in a catalytic converter. These are not stardust, they are forged in events of unimaginable violence, and for decades we believed we had found the sole source. When two neutron stars, the ultra-dense cores of dead stars, spiral together and collide, they create a cataclysm known as a kilonova. In that brief, blinding flash, conditions become so extreme that a rapid neutron capture process, or the R process, can occur. Atomic nuclei are bombarded by a flood of free neutrons, allowing them to glom on almost instantaneously, building up elements like gold, platinum, and uranium in a matter of seconds. This has been considered the primary cosmic factory for the universe's heaviest elements, but a provocative question now lingers in the minds of astrophysicists. Could the environments around supermassive black holes also serve as these extreme forges? The key to the R process is an overwhelming abundance of free neutrons. You need a place that is incredibly hot, dense, and crucially rich in neutrons but relatively poor in protons. This neutron-rich soup is where heavy elements can be assembled before radioactive decay tears them apart. Some of the most energetic outflows from active galactic nuclei might just provide this recipe. Picture the fierce winds blowing off the surface of a superheated accretion disk, or the turbulent soup of material in the aftermath of a tidal disruption event where a star has just been shredded. Theoretical models suggest that in these maelstroms, certain nuclear reactions could produce the necessary flood of neutrons. If the conditions are just right, the R process could ignite within these black hole-powered outflows, spraying newly forged heavy elements into the surrounding galaxy. This material would eventually cool, mix with interstellar gas, and become incorporated into future generations of stars and planets. It is a staggering thought. The same engine that can shut down star formation across a galaxy might also be secretly seeding it with the precious ingredients for rocky planets and ultimately for life. The gold in your jewelry may have been born in the aftermath of a neutron star collision, a spectacular and rare event, but some of it might have a far more ancient and monstrous origin, forged in the winds of a quasar that shone billions of years before our sun even ignited. This possibility transforms the black hole from a mere destroyer or regulator into a potential creator of cosmic wealth, subtly enriching the chemical future of everything that forms in its wake. This hidden forge of creation exists within a darkness so absolute we believed it could never be seen. Yet one of the most profound secrets is that we have now looked directly into the abyss and captured its portrait. The supermassive black hole has a shadow, and we have photographed it. This monumental achievement belongs to the Event Horizon Telescope, a planet-sized observatory created by linking radio telescopes across the globe, from the mountains of Hawaii to the peaks of the Andes, even to the South Pole. Together, they formed a virtual dish as large as Earth itself, with a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. Their target was the heart of a giant elliptical galaxy called Messier 87, 55 million light-years away, home to a supermassive black hole known as M87 star, weighing in at a staggering 6.5 billion solar masses. The iconic image they revealed in 2019 was not the black hole itself. No light can escape from beyond the event horizon to show us that. What we see is something even more telling: its shadow. This dark central region is a silhouette, an absence of light carved out against the brilliant, swirling backdrop of the black hole's superheated accretion disk. But the physics at play here bends reality itself. The black hole's immense gravity acts as a lens, warping the path of the light coming from the disk behind it. This gravitational lensing magnifies and distorts the image, wrapping the light from the far side of the disk up and around the shadow, creating that now famous ring of fire. The ring is not perfectly symmetrical. One side is noticeably brighter than the other. This brilliant crescent is a direct signature of a ferociously spinning black hole. The material on the side of the disk that is rotating toward us, thanks to the relativistic effects of its near light-speed motion, appears boosted and brighter. The material spinning away from us is dimmed. This Doppler beaming, combined with the lensing, creates that lopsided glow, confirming that M87 star is not just a massive pit, but a dynamic, spinning vortex. That single, grainy, orange donut is more than a triumph of engineering. It is a direct test of Einstein's general relativity in the most extreme gravitational environment we have ever probed. The size and shape of the shadow match the predictions of his century-old equations with stunning precision. It opens an entirely new window onto the universe, a field now called black hole astronomy. We are no longer just inferring these monsters from their effects on stars and gas. We are starting to see the very architecture of space-time twisted around them. This is not the end of observation, but the beginning. The same global telescope has since turned its gaze to our own galactic center, Sagittarius, a star producing its shadowy portrait. With each new image, and as we add more telescopes to the array, we will watch these shadows change and flicker as they feed, testing the limits of physics and peering deeper into the darkness to understand the engines that shape our cosmos. That shadow is a portrait of a mature, billion solar mass giant, but the black hole family tree has a glaring, mysterious gap. Between the stellar mass black holes born from dying stars and the supermassive behemoths at galactic centers, there should be an entire class of missing links. These are the intermediate mass black holes, and their elusive nature is one of the great detective stories in modern astronomy. Why does this gap matter so profoundly? Because if supermassive black holes grew from smaller seeds, then these intermediate monsters are the crucial middle step, the adolescent phase in the life cycle of a cosmic giant. Finding them would be like discovering the fossil record that connects dinosaurs to birds, a direct line of evidence showing how the largest structures in the universe assembled themselves over time. But spotting them is incredibly tricky. They are not massive enough to whip stars into the easily observed, frantic orbits we see at the center of the Milky Way. And unlike their supermassive cousins, they are not usually surrounded by enough gas to shine as brilliant, unmistakable quasars. They are the cosmic quiet ones, the introverts hiding in plain sight. So where do astronomers hunt for these ghosts? Two primary hiding places offer promising clues. The first is within the ancient, dense balls of stars known as globular clusters. These are relics from the early universe, orbiting galaxies like swarms of stellar bees. Some of these clusters show a curious concentration of stars at their very core, stars moving just a little too fast, as if tugged by an invisible, dense mass. The second candidate location is the heart of small, dwarf galaxies. If a supermassive black hole grows with its galaxy, then a tiny galaxy should host a proportionally smaller, intermediate mass black hole. The detective work involves painstaking observation. Astronomers use powerful telescopes to map the subtle, high-speed dance of stars at the center of a candidate dwarf galaxy or globular cluster. They look for the telltale sign of stars orbiting something massive and completely dark. Another method is to listen for a burp of X-rays. Occasionally, a star or gas cloud might wander too close to a dormant intermediate black hole, getting torn apart and creating a brief, bright flare of high-energy radiation. A single, faint scream in the X-ray spectrum that announces its presence. One of the most compelling candidates to date came from such a flare, detected in a galaxy far from any obvious center, suggesting a wandering intermediate mass black hole. Each potential discovery is met with intense scrutiny, as other explanations, like a tight cluster of neutron stars, must be ruled out. The hunt for these missing links is more than cataloging cosmic oddities. It is a search for the very growth mechanism of the universe's most powerful objects. Did supermassive black holes grow steadily from small seeds by feeding, or did they leap in size through dramatic mergers? Finding a population of intermediate black holes and measuring their masses would provide the missing chapters in that story, revealing whether the giants at the center of galaxies were built by a lifetime of steady meals or by a few colossal cosmic collisions. The hunt for those missing links connects to a mystery far larger than black holes themselves. Our 18th secret ventures into the most profound cosmic speculation of all. Supermassive black holes, or their ancient, invisible cousins, might hold the key to explaining dark matter. For decades, we have known the universe is built on a hidden scaffold. Galaxies spin too fast to be held together by the gravity of their visible stars and gas alone. Vast clusters of galaxies bend light with the strength of an invisible, massive presence. We call this ghostly, unexplained mass dark matter, and it makes up about 85% of all the matter in the cosmos, but we have never directly detected a single particle of it. This glaring gap has led cosmologists to consider a radical alternative. What if dark matter isn't made of exotic, unknown particles, but of ordinary, albeit invisible, astrophysical objects? Primordial black holes are a perfect candidate. These would not be the black holes born from dying stars, but ones forged in the incredible density fluctuations of the universe's first second, a potential byproduct of the Big Bang itself. They could span a vast range of sizes, from as small as an asteroid to thousands of times the mass of our Sun. A vast population of these primordial black holes, drifting like invisible icebergs through the cosmic sea, could provide the unseen gravitational glue that holds galaxies together. The idea is beautifully elegant. It solves two profound mysteries with one stroke, explaining both the seeds of supermassive black holes and the nature of dark matter. But science demands evidence, and here the arguments face serious constraints. The primary tool for hunting these invisible objects is called gravitational microlensing. If a primordial black hole passes directly between Earth and a distant star, its gravity will act as a tiny lens, briefly magnifying the star's light. Astronomers have conducted massive, years-long surveys, monitoring millions of stars in nearby galaxies like the Magellanic Clouds. They have seen microlensing events, but not nearly enough to account for all dark matter if it were made of black holes in certain mass ranges. These surveys have effectively ruled out primordial black holes making up all dark matter if they are between roughly the mass of the Moon and about 100 solar masses. Another powerful constraint comes from the cosmic microwave background, the faint afterglow of the Big Bang. If a large number of primordial black holes existed in the early universe, their formation and subsequent evaporation through Hawking radiation would have injected extra energy into the primordial soup, altering the precise temperature patterns we observe in that ancient light. The pristine agreement between theory and observation places tight limits on how many could have existed. So is the case closed, not entirely. Windows remain. Primordial black holes could still constitute all dark matter if they are either very small, on the scale of asteroids, or incredibly large, in that elusive intermediate mass range of hundreds to thousands of solar masses. These sizes evade the current microlensing and cosmic background constraints. Furthermore, they could make up a significant fraction, if not all, of the dark matter in certain regions, like the dense cores of galaxies. This secret does not offer a definitive answer, but it highlights a breathtaking possibility. The most dominant form of matter in the universe might not be a sea of unknown particles, but a hidden population of ancient black holes, fossils from the first chaotic moment of creation. It means the monsters at galactic centers could be the most visible members of a vast, dark family, the rare giants that grew up in the light, while countless smaller, darker siblings shape the cosmos from the shadows. This connection keeps black holes at the very heart of cosmology's greatest mystery, a reminder that the key to understanding the universe's hidden skeleton might lie in the nature of its most profound darkness. The most violent birth in the universe can produce a cosmic fugitive. Our 19th secret reveals that a supermassive black hole can be thrown from its own galaxy, becoming a rogue, homeless giant drifting through the eternal void. This astonishing event is the ultimate recoil, a gravitational kick born from the final, chaotic moments of a black hole merger. When two supermassive black holes spiral together and finally become one, they do not simply merge in silence. They churn space-time, sending out ripples of gravitational waves. If the merger is lopsided, with black holes of unequal mass or misaligned spins, the emission of these waves is not symmetrical. More waves shoot out in one particular direction. Just as a rifle kicks back against a shooter's shoulder, the newborn black hole recoils in the opposite direction from that burst of waves. This is no gentle nudge. The mathematics of general relativity shows these kicks can reach thousands of kilometers per second. At the upper end of this scale, the velocity is so immense it can exceed the escape velocity of even the largest galaxies. The black hole, this billion solar mass engine, is literally shot out of its home, carrying with it any accretion disk and jet system it had at the moment of ejection. For a time, it would streak through intergalactic space as a displaced quasar, a brilliant beacon with no galaxy around it, until its fuel supply eventually ran dry and it faded back into darkness. While we have not yet conclusively caught one of these hypervelocity black holes in the act of escape, we may have seen their calling cards. Astronomers have discovered stars moving at impossible speeds, streaking through the Milky Way's halo so fast they are unbound from our galaxy entirely. These hypervelocity stars are traveling over 1,000 kilometers per second, fast enough to eventually leave the Milky Way forever. The leading theory for their origin is a dramatic encounter with our own galactic center. If a binary star system wandered too close to Sagittarius, a star, the supermassive black hole's gravity could capture one star and violently fling the other away like a stone from a slingshot. But there is another, even more spectacular possibility. What if the slingshot itself was thrown? If a recoiling supermassive black hole was ejected from the core of a merging galaxy, the titanic gravitational disturbance of its exit could have flung entire clusters of stars along with it, sending them racing into the void as a final, fleeing entourage. Finding a hypervelocity star, or better yet, a group of them on a similar trajectory, could be the faint tracer bullet pointing back to a cataclysmic kick that happened millions of years ago. These rogue black holes, if they exist, would be the ultimate loners, carrying the story of a galactic collision within them as they journey forever through the cold, empty spaces between the islands of light. The ultimate recoil of a rogue black hole is a cosmic explosion of gravity, but the true explosion of our understanding happens at the very center of these monsters. Secret 20 forces us to confront the greatest secret of all, the complete and utter breakdown of physics itself. For all their power and grandeur, our description of a supermassive black hole contains a fatal flaw, a point where our most trusted theory of the universe simply gives up. General relativity, Einstein's masterpiece, predicts with cold certainty that at the very core of a black hole, all the collapsed matter is crushed into a single point of zero volume and infinite density. This is the singularity. The equations blow up to infinity, and the laws of space, time, and causality cease to have any meaning. It is a mathematical warning sign, a glaring red flag that tells us our understanding of gravity is incomplete. We have reached the edge of the map, and the inscription reads, "Here be dragons." The problem is that infinities do not exist in nature. They are a sign that a theory has been pushed beyond its limits. General relativity is a theory of the very large, the cosmic dance of planets, stars, and galaxies. But the singularity is unimaginably small, a realm where the quantum rules of the very small must take over. To resolve this paradox, to understand what truly lies at the heart of a black hole, we need a theory that does not yet exist in a complete form, a theory of quantum gravity. This would be the holy grail of physics, a framework that seamlessly unites Einstein's relativity with the bizarre, probabilistic rules of quantum mechanics. Without it, the singularity remains the ultimate cosmic question mark. But physicists are not content to leave a blank space on the diagram. They use the hints from partial theories to imagine what might replace that point of infinity. One compelling idea comes from loop quantum gravity, a candidate for quantum gravity. It suggests that the collapse of matter does not proceed forever. Instead, at an incredibly tiny scale, a trillion times smaller than an atom, a repulsive force from the quantum structure of spacetime itself kicks in. The collapse halts and the matter rebounds into a hypothetical object called a Planck star. This would not be a singularity, but an ultra-dense yet finite ball of matter. From our perspective outside the event horizon, this rebound would take billions of years due to the extreme time dilation, meaning every black hole we see could, in its own frame of reference, already be an expanding Planck star, a universe in a bottle. String theory, another path to quantum gravity, proposes a different solution, the fuzzball. In this view, the black hole is not empty space with a point mass at the center. Instead, the entire region inside the event horizon is filled with a tangled, vibrating ball of strings, the fundamental threads of reality in string theory. The event horizon becomes a fuzzy, transitional surface, and the terrifying singularity simply vanishes, replaced by this complex quantum gravitational entity. These are not observations, they are prophecies from mathematics, glimpses of a deeper reality. They tell us that the heart of darkness is not an end but a frontier. The singularity is not an answer, it is the most important question we can ask, a cosmic signpost pointing toward a deeper layer of reality where our current laws of physics are merely an approximation. What lies beyond that point of infinite density might be the key to a theory of everything. That mathematical frontier of the singularity is a question for the future, but these giants offer a direct window into the past. Supermassive black holes in their brilliant quasar phase illuminate the early universe. Think of them not just as monsters, but as the most powerful cosmic lighthouses ever created. Their light, generated in the furious accretion disks of black holes that shone when the cosmos was just a few 100 million years old, must travel across billions of light years to reach us. On that unimaginably long journey, it does not travel through empty space. It passes through the vast, diffuse clouds of gas that float in the voids between galaxies, the intergalactic medium. This is where the magic happens. As the quasar's intense beam of light pierces these ancient gas clouds, the gases absorb very specific wavelengths of that light. Each element has a unique fingerprint, a pattern of absorption lines that gets imprinted onto the quasar's spectrum, the rainbow of its light broken into a detailed barcode. When astronomers capture that spectrum, they are not just seeing the quasar, they are reading a fossilized record of everything its light passed through. The most profound signature is from neutral hydrogen, the primordial fuel of the universe. It creates a distinctive series of absorption lines known as the Lyman alpha forest. This forest is not a single line, but a thicket of hundreds of individual absorption features, each one representing a different cloud of hydrogen at a different distance, and therefore from a different time in cosmic history. By studying the density and distribution of this forest, scientists can map the large-scale structure of the early cosmos, tracing the filaments of the cosmic web when it was just beginning to form. But the story gets even richer. In the spectra of slightly younger quasars, astronomers sometimes find the fingerprints of heavier elements like carbon, oxygen, and silicon. This is astonishing. These elements, which astronomers call metals, did not exist in the Big Bang. They were forged in the cores of the first stars and scattered by their supernova explosions. Finding their absorption lines in the intergalactic medium means that the fierce light of a quasar is illuminating the pollution from those first stellar generations. It allows us to date and study the era of the first stars, an epoch we can observe in no other way. So a quasar's light is a dual probe. It reveals the pristine conditions of the primordial universe in the hydrogen forests, and it also lights up the aftermath of the first acts of cosmic creation in the faint traces of early metals. These black hole beacons turn the entire universe into a vast laboratory, letting us conduct chemistry and physics experiments on gas clouds so distant and ancient they are almost as old as time itself. The universe's most powerful light hours illuminate the past, but their very existence forces us to rewrite the fundamental laws that govern reality. Secret 22 reveals these cosmic giants challenge the bedrock principles of thermodynamics. For centuries, these laws seemed inviolable. Energy cannot be created or destroyed, only transformed. The total disorder or entropy of a closed system always increases. And absolute zero, the point where all molecular motion stops, can never be reached. Then black holes entered the equations and everything changed. The problem was stark. If you throw a box of hot gas, a highly ordered, low-entropy system, into a black hole, it vanishes from our universe. According to classical physics, the black hole's mass increases, but all the intricate information about that gas, the positions and velocities of its trillions of molecules, is lost forever. The entropy of the universe appears to have decreased, a direct violation of the second law of thermodynamics. This paradox troubled a young physicist named Jacob Bekenstein. His radical solution was to propose that black holes themselves must possess entropy, and a tremendous amount of it. He suggested a black hole's entropy is not proportional to its volume, but to the surface area of its event horizon. The larger the black hole, the greater its hidden disorder. This was a conceptual earthquake. An event horizon is not a physical surface, but a mathematical boundary. Yet Bekenstein argued it could store information like a cosmic hard drive, with each tiny plank-sized area on the horizon acting as a fundamental bit. This preserved the second law. When the hot gas falls in, the black hole's mass and its event horizon area grow, increasing its entropy by an amount that more than compensates for the lost entropy of the gas. Total universal disorder still goes up, but this brilliant fix created a new and even more shocking implication. In thermodynamics, any object with entropy must also have a temperature. And any object with a temperature must emit radiation. This was seemingly impossible. Nothing escapes a black hole. Enter Stephen Hawking. He combined quantum mechanics with general relativity and made the most startling prediction in modern cosmology. The vacuum of space, he realized, is not empty. It is a seething quantum foam where pairs of virtual particles, one matter and one antimatter, constantly pop into existence and almost immediately annihilate each other. Hawking's genius was to imagine this happening right at the edge of an event horizon. If the particle pair is created such that one falls in while the other escapes, the black hole effectively radiates. This Hawking radiation is incredibly faint for a supermassive black hole, a whisper of heat against the cosmic microwave background. But its existence means black holes are not truly black and they are not eternal. They have a temperature and they slowly evaporate. The smaller the black hole, the hotter it glows and the faster it evaporates. For a stellar mass black hole, this process would take longer than the current age of the universe. For a supermassive giant, the timescale is so astronomically vast it borders on the infinite. Yet the principle stands. These monsters are not simple, dead voids. They are complex thermodynamic objects with entropy, temperature, and a finite, if unimaginably long, lifespan. Hawking's revelation forged an unexpected link between the three great pillars of physics: gravity, quantum mechanics, and thermodynamics, suggesting they are all facets of a deeper, unified truth. The darkness at a galaxy's heart, therefore, is not a cold pit. It is a warm, if faintly glowing, thermodynamic engine, slowly ticking down across eons we cannot comprehend. That faint thermodynamic glow from a monster like ours is a whisper compared to the roar it once unleashed. The supermassive black hole at the heart of our own galaxy is a quiet neighbor, but its past is written in violence across the sky. Sagittarius, a star with its 4 million solar masses, sits in a deceptive calm today, a slumbering giant detectable only by the frantic orbits of stars around its invisible grip. Yet this peaceful present belies a cataclysmic history. Evidence suggests that just a few million years ago, a cosmic blink in galactic time, our black hole was a brilliant, active quasar. The most stunning proof of this ancient outburst isn't in the center itself, but in the vast structures that tower above and below the Milky Way's disk. These are the Fermi bubbles, first detected by NASA's Fermi Gamma-Ray Space Telescope. They are two colossal lobes of ultra-hot gas, each stretching 25,000 light-years from the galactic center, glowing in the highest energy gamma rays. Picture a giant, symmetrical hourglass of seething plasma, with our entire solar system nestled in one of its quiet outer walls. These bubbles are fossils, the ghostly imprint of a titanic eruption. The leading theory is direct and staggering. Between 1 and 3 million years ago, Sagittarius, a star, experienced a major feeding event. A vast cloud of gas, perhaps from a disrupted star cluster or an infalling dwarf galaxy, spiraled into its maw. As the black hole feasted, it didn't just shine, it blasted. The same mechanisms that power relativistic jets in distant quasars ignited. But instead of narrow beams, this may have been a more spherical, explosive outflow, a colossal burp of energy from the galaxy's core. The eruption funneled unimaginable amounts of energy into the galactic halo, inflating these giant bubbles and filling them with particles accelerated to near light speed. That energy is still there, trapped in the form of magnetic fields and ultra-hot gas, which continues to collide with the cooler galactic medium, producing the gamma rays we see today. This secret transforms our understanding of home. Our Milky Way is not a perpetually serene spiral. It is a system with a heartbeat, a rhythm of long slumbers punctuated by brief, catastrophic awakenings. The Fermi bubbles are the lingering scar of the last major eruption, a reminder that the monster in our basement is not dead, only resting, and if it woke once, it can wake again. The next great feast for Sagittarius, a star, might come from the eventual collision with the Andromeda galaxy billions of years from now, or from a closer, more unpredictable encounter with a gas cloud already drifting toward the center. Our quiet backyard holds the memory of a brilliant, violent youth and the potential for a similarly spectacular future, but a scar on the sky is a static monument. To truly understand the monster, we must ask it to perform. Our 24th secret reveals these giants are not just objects in the cosmos, they are its ultimate laboratories. A supermassive black hole provides a unique, natural testbed for the most extreme physics imaginable, a place where we can conduct experiments no particle accelerator on Earth could ever replicate. Every phenomenon we observe around them, from the bending of starlight to the faint glow of evaporation, is a direct test of our fundamental theories of reality. Take gravitational lensing, the warping of light by mass. Around a black hole, this is not a subtle effect. It is magnified to the extreme, creating multiple images of background stars, stretching them into arcs and wrapping the light from the accretion disk into that iconic ring. By meticulously measuring these distortions, astronomers perform precision tests of Einstein's general relativity. Does the bending of light match the predictions exactly, even in this ferocious gravitational field? Any deviation, any tiny crack in the prediction, would be a monumental discovery pointing toward new physics beyond Einstein. Then there is frame dragging, the twisting of spacetime itself by a rotating black hole. This effect, though subtle, has been measured around Earth with orbiting gyroscopes, but around a supermassive black hole, it is the dominant force in the ergosphere. The frantic orbits of stars and gas close to the event horizon carry the imprint of this spacetime whirlpool. By tracking these orbits over years, we can measure the black hole's spin with increasing precision, testing the specific predictions of general relativity for rotating masses. The data so far confirms Einstein's brilliance, but the search for any anomaly continues. The most profound laboratory experiment, however, involves a prediction that has never been directly observed: Hawking radiation. Detecting the faint thermal glow from a stellar mass or supermassive black hole is currently impossible against the cosmic background, but physicists are ingenious. They create analog black holes in laboratories using sound waves in superfluid helium or light in optical fibers. In these setups, a horizon forms where the flow of the medium exceeds the speed of sound or light within it. Experiments have already detected the analog of Hawking radiation in these systems, lending credence to the theory that real black holes must evaporate. These analog experiments bridge the gap between quantum mechanics and gravity, offering tangible clues about what happens at that perilous edge. Each observation, each precise measurement, is a probe sent into the interface between the very large and the very small. A supermassive black hole is where the classical, smooth geometry of general relativity must somehow shake hands with the fuzzy, probabilistic world of quantum mechanics. Any inconsistency we find there is not a failure, but a flashlight, illuminating the path toward a deeper, unified theory of everything. In this way, the darkest objects in the universe become our brightest beacons for discovery, transforming the abyss into a chalkboard where the cosmos writes its deepest laws. These cosmic laboratories lead us to the final, and perhaps most profound, secret of all. The ultimate truth hidden in the heart of a supermassive black hole could be the master key that unlocks a complete understanding of the universe. This grand secret revolves around a single, maddening puzzle, the black hole information paradox. It is a conflict between our two most successful theories, and its resolution is believed to be the crucial step toward a theory of everything. On one side stands quantum mechanics, the rulebook for the subatomic world. It states with absolute certainty that information is never truly destroyed. If you burn a book, the ash and smoke still contain, in principle, all the information needed to reconstruct every word. The information is scrambled, but it persists. On the other side stands Einstein's general relativity, which describes gravity and the cosmos. It paints a stark picture of a black hole. When something falls in, all the information about that object, its composition, its shape, its history, vanishes from our universe behind the event horizon. According to classical relativity, if you wait long enough for the black hole to evaporate via Hawking radiation, all that emerges is a featureless thermal glow. The original information is gone forever. This is the paradox. Two foundational pillars of physics make contradictory predictions about the most basic property of reality. Either information is lost, breaking quantum mechanics, or it is preserved, forcing us to rewrite our understanding of gravity and black holes. For decades, this was seen as a fascinating but abstract problem. Then, physicists realized its staggering implication. The clash is not a bug, it is a feature. It is the universe screaming at us that our theories are incomplete where they meet, at the singularity and the event horizon. Resolving this paradox, understanding how information escapes or is encoded, requires a theory that seamlessly merges gravity with quantum mechanics, a theory of quantum gravity. This would be the long-sought theory of everything, a single framework capable of describing every force and particle in the cosmos, from the whirl of galaxies to the flutter of a butterfly's wing. And black holes are the only place in the universe where the effects of such a theory are magnified to a scale we might eventually observe or deduce. Think of them as cosmic Rosetta Stones, just as the original stone bore the same text in 3 scripts, allowing scholars to crack ancient Egyptian hieroglyphs. A black hole presents the same physical reality described by 2 conflicting scripts, quantum mechanics and general relativity. By learning to read the translation between them, by deciphering how information is truly handled, we can uncover the unified language of reality itself. Current ideas are breathtaking. The holographic principle suggests that all the information about everything within a black hole's volume is not stored inside, but is painted like a hologram on its 2-dimensional event horizon. The information never falls in, it is smeared across the surface. Another idea posits that the chaotic connections between particles in Hawking radiation itself hold the scrambled code, meaning the information leaks out slowly over the eons of evaporation. Each proposal is a step toward that grand unification. This final secret elevates the supermassive black hole from a monster, an engine, or a regulator to the most important object in theoretical physics. It is the ultimate cosmic crucible where the deepest laws of existence are being forged and tested. The darkness at the center of a galaxy is not an end. It is the most compelling question mark in the cosmos, a silent challenge that, once answered, will illuminate everything. From their paradoxical brilliance to the quantum whispers at their event horizons, we have traveled through 25 astonishing secrets. We have seen how these monsters are not black but blindingly bright, how they may have formed before galaxies themselves, and how they act as cosmic architects, regulating star formation and even forging the heaviest elements. We have watched them devour stars, launch jets across millions of light years, and potentially hide bridges to other realities within their singularities. We have heard their gravitational hum and glimpsed their dark shadows, all while confronting the ultimate truth that they are laboratories where physics itself breaks down, pointing us toward a theory of everything. Yet for every secret we uncover, a dozen profound questions emerge. Are they portals or prisons? Did they build the galaxies or were they built by them? Could they be the dark matter we have sought for decades? The journey does not end here, it simply deepens. The universe's greatest mysteries are not in the distant void. They are lurking in the hearts of galaxies, waiting to be understood. What do you think is the most mind-blowing secret of all? Let us know in the comments below, and do not forget to subscribe as we continue to explore the cosmos's deepest enigmas.